9.6 Lesson 1, the ratio test. We have 3 objectives for our lesson today. 1, you'll be able to apply the ratio test to determine the convergence or divergence of a series with non-zero terms. 2, you will know when the ratio test is inconclusive. So if that's the case, you have to use some other test to determine the convergence or divergence of the given series. And at the end, we'll take a look at the proof of one property from the ratio test. So our vocabulary today is the ratio test. So here we have the ratio test. You can apply it to any series with non-zero terms. So what is it that you need to do to apply the ratio test? So you need to find a limit. And the limit that you need to find is right here. And you have 1, 2, and 3 from the ratio test. And in all of them, you're finding the same limit. So you always find the same limit. But depending on the value of the limit, you will reach different conclusions using the ratio test. So if the limit is less than 1, then you may conclude using the ratio test that your series converges absolutely. If the limit is greater than 1 or infinity, you may conclude using the ratio test that the series diverges. However, if you find that the limit is equal to 1, you cannot reach any conclusion using the ratio test. The series could be convergent or it could be divergent, so you have to find out using something else that we've learned. We most often use the ratio test for series whose nth term involves a factorial expression or an exponential expression, as we will see now as we look at some examples. As I just noted, we find the ratio test to be particularly useful for series whose nth terms involve exponential expressions and factorial expressions. And our first example is a case of that. You have that the nth term is 2 to the n, which is an exponential expression, divided by n factorial. So how do you use the ratio test? And first of all, can you use the ratio test? It's a very low bar. You just have to have a series with non-zero terms. And this is a series with non-zero terms. So we can use the ratio test. Although it has a low bar for usability, it may not necessarily be the easiest test to apply. Or maybe it's not something that's going to work out very well because it may not be easy for you to find the limit, or perhaps you find that the limit is equal to 1, in which case the ratio test cannot be used. Most often, though, the limit's probably not too hard to find. But you could have a problem if it's equal to 1, then you'd have to do something else. So let's go ahead and take a look at how we set up the limit. Again, you always find the same limit, you just reach different conclusions based on what that limit is equal to. So we'll begin by setting up the limit for our example problem. So here we have the limit where we're taking the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. So here we have the nth term, which we have in the denominator of our quotient. And in the numerator of our quotient, we have the n plus 1th term, where we replace the n in the nth term with n plus 1. So now you just have to go ahead and find this limit. Now, one thing to note is that you don't need the absolute value in this case because both the n plus 1th and the nth terms are going to be positive. So in the next step, we can simplify by removing the absolute value because the quotient is going to be positive to begin with. So you see that I no longer have the absolute value, and you also see that I have rewritten the division as multiplication. How do you divide? You multiply by the reciprocal of the divisor, and that's what I've done here. The next step is to cancel any common factors that you may have. So we're going to rewrite 2 to the n plus 1 using properties of exponents, and we're also going to rewrite n plus 1 factorial using the definition of n factorial. So 2 to the n plus 1 can be written as 2 to the n times 2 to the first. You have a product of two powers with the same base, so you can add the exponents. And n plus 1 factorial is 1 times 2 times 3 times all the way to n times n plus 1. But all the way to n would be just n factorial, and you have one extra factorial, one extra factor in n plus 1 factorial, and that would be the factor n plus 1. So n plus 1 factorial is n factorial times an extra factor n plus 1. So doing that, we're now able to cancel the common factors of n factorial and 2 to the n. So what does that leave us? It leaves us with this. The limit as n approaches infinity of 2 over n plus 1. And as n goes to infinity, 2 over n plus 1 will go to 0. And when you look here at the ratio test, we have found that our limit is less than 1, because we found that our limit is 0. And because it's less than 1, we may conclude that the series that we began with converges absolutely. So here we're looking at number 16, determine the convergence or divergence of the series using the ratio test. One thing to note is that this is not a geometric series. And the reason why it's not a geometric series is because of the n that you have here. So you cannot use the geometric series test. But the instructions say determine the convergence or divergence of the series using the ratio test. So we'll go ahead and do that. So again, as long as you have a series with non-zero terms, you can try the ratio test. So we'll go ahead and do that. And we need to find this limit and figure out what that limit is equal to. And based on what the limit is equal to, we will reach an appropriate conclusion. And if the limit is equal to 1, no conclusion can be drawn. You have to do some other test. So here is how we set up the limit. We need to find the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. So in the numerator, I have the n plus 1th term. I just replace n with n plus 1. And in the denominator, I have the nth term, which is as it is given in the series. So now I need to simplify. The first thing that I can do in my simplification process is to recognize that these quantities are going to be positive for all values of n from n is equal to 1 to infinity. And in fact, we're considering what happens as n goes to infinity. So both my numerator and denominator will be positive, and because of that, I can remove the absolute value signs. The next step in the simplification is to rewrite the numerator using properties of exponents so that we can cancel common factors that we have in the numerator and the denominator. So here we have a product of two powers with the same base. So when you add the exponents, this is the same as what we had in the previous step. But now we can cancel the common factor of 3 over 2 to the n that we have in the numerator and the denominator, which would leave us with the limit as n approaches infinity of 3 over 2 times n plus 1 over n. And 3 over 2 is a constant, so you could factor it out of the limit. So you would have the limit as n approaches infinity of n plus 1 over n, which is equal to 1 because the degree of the numerator and the degree of the denominator are the same. So the limit of a rational expression in which the degree of the numerator is the same as the degree of the denominator is simply the quotient of the leading coefficients. 1 divided by 1 is 1. So 3 over 2 times 1 is 3 over 2. Don't forget the 3 over 2. So the limit is 3 over 2, and 3 over 2 is greater than 1. So we may conclude by the ratio test that this series diverges. Here we have an alternating series, and we'd like to go ahead and use the ratio test. Can we use the ratio test? You can use it as long as you have a series with non-zero terms. And this is a series with non-zero terms. So we will begin by writing this limit, and then we will evaluate the limit, and depending on what we get for the limit, we will either reach a conclusion about the convergence or divergence of the series, or if the limit is equal to 1, we cannot reach a conclusion using the ratio test, and we would have to do something else, use another test. So here is the limit that we have, and again, in the numerator, you have the n plus 1th term, in the denominator, you have the nth term, and you're taking the absolute value of this quotient of the n plus 1th and the nth terms and taking the limit of that absolute value as n goes to infinity. And again, we can begin by thinking about the absolute value. When you look at the series that we are working with, we have a sub n, and then we have negative 1 to the n. So 2 to the 4n, for any n greater than or equal to 0, where n is an integer, will be positive. Same with 2n plus 1 factorial. So the quantity here is always going to be positive. What could make a term negative is the negative 1 to the n. But when you use the ratio test, you're taking the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. And because you're taking the limit of the absolute value of the quotient, you don't need this anymore, because that's the part that was responsible for giving you negative terms. But because you're taking absolute value, you won't have negative terms. So you can simplify your expression that you're taking the limit of by removing both the absolute value signs and the negative 1 to the n plus 1 and the negative 1 to the n. So you can see that I've done that here. And in addition to that, I also went ahead and distributed the 4 to the n plus 1 to get 2 raised to the power of 4n plus 4. And in the denominator here, I distributed the 2 to the n plus 1 to get 2n plus 2 plus 1 would be 2n plus 3 factorial. And how do you divide? You multiply by the reciprocal of the divisor, and that's what I've written here. So now the next step is to see if we can cancel any common factors that we have. So you want to simplify using properties of exponents and rewrite your factorial expressions. So you can rewrite 2 to the 4n plus 4 using properties of exponents, and you can rewrite 2n plus 3 factorial using the definition of factorial expressions. So we can write 2 to the 4n times 2 to the 4th, a product of two powers with the same base. When you add the exponents, you get the same as 2 to the 4n plus 4. And the 2n plus 3 factorial, that's 1 times 2 times 3 times 4 times all the way to 2n plus 1 times 2n plus 2 times 2n plus 3. Again, n factorial by definition is 1 times 2 times 3, and you keep going until you get to the integer n. So what's before the integer n? N minus 1. What's before that? N minus 2. And so on. So you have all the integers in between. So 2n plus 3 factorial is 1 times 2 times 3, and you go all the way to 2n plus 3, but what's one integer less than, what's 1 less than the integer 2n plus 3, 2n plus 2, and what's 1 less than the integer 2n plus 2, 2n plus 1. So 2n plus 3 factorial can be simplified to be 2n plus 1 factorial times 2n plus 2 times 2n plus 3. And of course this helps us because now we can cancel the common factors of 2n plus 1 factorial that we have here and from the other term, which I have written here in gold. And then we can also cancel the 2 times 4 to the n, which I have written here in gold, with the 2 times 4 to the n. What does that leave us? So this is what we have, the limit as n approaches infinity of 2 to the 4th, which is 16, and in the denominator, we're just left with these two factors. And if you multiply these two factors, you'll get 4n to the second power, and you have other terms that are smaller degree. So you have 4n to the second power, and then you have 6n plus 4n would be 10n, and then you have plus 6. But the significant thing is you have a constant in the numerator, and you have a quadratic term, a quadratic factor in the denominator with n. So as n goes to infinity, this limit will go, the expression will go to 0, and the limit will be equal to 0. And of course, 0 is less than 1, so we can conclude using the ratio test that our series converges absolutely. We would now like to take a look at the proof of property number 1 of the ratio test. So we have a series with non-zero terms, and we'd like to show that the series converges absolutely if we determine this limit to be less than 1. So this is the limit being less than 1 would be something that is known to us, and if we have that information, we need to, in our proof, argue beginning with the given information, which would be the limit being less than 1, and then argue logically until we reach the conclusion that we must have a series that converges absolutely. So let's take a look at that. And again, this is our starting point. So to prove property 1, we assume that we have the limit of the absolute value of the quotient of the n plus 1th and the nth terms as n approaches infinity be less than 1. And we'll say it's equal to some value r that's less than 1. And we're going to choose uppercase r so that it is also less than 1, but greater than lowercase r, which is whatever the limit is equal to. So what does it mean for this limit to be equal to r, lowercase r? It means that the further you go out for n, as n gets larger and larger, what that means is this quotient will get closer and closer to the limit lowercase r. So by the definition of the limit of a sequence, there will be some uppercase n greater than 0, such that, and all that means is for a large enough value of lowercase n, this quotient that we're taking the limit of as n approaches infinity will be less than uppercase r. In other words, it will be getting closer to lowercase r, and it'll be close enough to lowercase r so that it will be somewhere between lowercase r and uppercase r. And that has to happen because the limit exists. So we have that. So for some uppercase integer n greater than 0, the quantity that we're taking the limit of will be less than uppercase r. In other words, it'll be getting closer to lowercase r, which is the limit for all lowercase n values that are greater than this integer uppercase n, whatever that uppercase n may be. And of course, that will depend on how close you want this quantity to be to the limit lowercase r. Therefore, you can write the following inequalities. So let's take a look at what inequalities we're writing here. So you're looking at this absolute value of the quotient of the n plus 1th and the nth terms. And from the logic that we went over in the first paragraph there, for all integers n uppercase, for all integers n greater than uppercase n, this quantity that we're taking the limit of will have to be less than uppercase r. In other words, it's getting close enough to the limit because we've gone out far enough for n. So what that means is we will have this. We will have the absolute value of a sub n plus 1 over a sub n, and that's going to be less than uppercase r. So you can simplify the left side so that you'll have absolute value of a sub uppercase n plus 1 divided by the absolute value of a sub uppercase n. And then you can multiply both sides of this inequality by the denominator of the left side, and that would give us this particular inequality. And that's what we have here. Now we repeat by replacing n in the denominator with uppercase n plus 1, so the index of the term in the numerator will be n plus 2. And we can repeat the process that we did in the first step by multiplying both sides of this inequality by the denominator of the left side. And when we do that, we will get this. So on the right side, we will have the absolute value of a sub uppercase n plus 1 times r, and when we multiply by the denominator of the left side of the inequality, it will cancel the denominator on the left side. So we will have this. Now you will make an observation here. The observation is this. When you look at this inequality that I have here, which you see here, what do you notice? Well, you'll see that you have the absolute value of a sub n plus 1. Where do you see that before this line? You see that on the first line. But now we're multiplying it by uppercase r. So what we do is we say, well, if you look at what we had before and we multiply both sides of that inequality by uppercase r, which is positive, this is what we will have. So now we're able to do the following. I'm just going to take what we already have here and write it a little bit further to the left. But now what I have here matches what I have here, and I know that to be less than the absolute value of a sub uppercase n times r squared. And that's what I have here. When you repeat the process, you get the lines that are below that. So now we focus on the parts that I am circling in gold. And if you look at these, they form the terms of a geometric series whose common ratio is uppercase r. And that's what we write here. The geometric series that you see with the last terms in each of these inequalities, how do we know that it converges? We know that it converges because the common ratio is uppercase R, and if you go back to this line from the proof, we see that uppercase R is greater than 0 and less than 1. So this is a geometric series that must converge because the absolute value of its common ratio is between 0 and 1. And now we're going to employ the direct comparison test to reach a conclusion about another series. So the direct comparison test states that if you have two series whose terms are positive and the terms of one series are smaller than the corresponding terms of a series that is known to converge, then that series that we're considering must also converge. So we know that this is a geometric series that converges, and if you look at each of these inequalities, you are doing a direct comparison between the terms of your convergent geometric series and the terms of another series. And because this other series has terms that are smaller than the corresponding terms of the convergent geometric series, this other series must converge by direct comparison to the convergent geometric series. And that's what we're stating here. And so by the direct comparison test, this series also converges. And look at how we describe the nth term of that series. It's described as the absolute value of a sub uppercase n plus lowercase n, where lowercase n goes from 1 to infinity. So the very first term would be this, and then we have the next term, and so on. So by the argument that we just went over, we know this particular series must converge by direct comparison to the convergent geometric series that we examined earlier. So as we set up for the conclusion of the proof, we'd like to go back and review what we've done so far. We're trying to show that if we know this limit to be less than 1, we're trying to show that the series must converge absolutely, where the series under consideration has non-zero terms. So how do we conclude our proof? How do we show that this must be the case? So take a look at the series that we've just shown converges by direct comparison to the convergent geometric series. The series that's under consideration is this one here. We can say from n is equal to 1 to infinity. What is the difference between this series that is under consideration and the series that we've shown must converge by direct comparison to the convergent geometric series? The series that we've shown must converge is the same series as this one, except it's missing the first uppercase n minus 1 terms. It's the same series without the first uppercase n minus 1 terms. So this doesn't make a difference for convergence, because convergence is considering what happens as n goes to infinity. So if you're missing a finite number of terms, it doesn't matter. So that's why it states here, thus, this in turn implies that the series here converges. Now, there is one difference between what we were considering in the statement of the ratio test, which is that you have a signed series, and what we are considering here is the corresponding absolute value series. So that is one difference. But the corresponding absolute value series must converge because getting rid of a finite number of terms from the beginning of that series will not have an impact. So again, we're considering the corresponding absolute value series. So we know this corresponding absolute value series must converge. So what does knowing that the corresponding absolute value series converges tell us about the original series that is under consideration in the ratio test. So we've come this far in the proof. We know that because this series is known to converge, it doesn't matter that we're getting rid of the first uppercase n-1 terms from this series, which is the corresponding absolute value series, to the one that is under consideration in the ratio test. So what does it mean that we now know that this corresponding absolute value series converges? By theorem 9.16, if the corresponding absolute value series converges, then the original sine series must also converge. So consequently, by theorem 9.16, the original sine series must converge absolutely, that is by definition. You can see here that a sine series is absolutely convergent if its corresponding absolute value series converges. So we have shown by theorem 9.16 that the sine series must converge absolutely. So that's the proof of property 1 of the ratio test. And again, the structure of the proof is what we've already gone over, but I'd like to conclude by going over the structure of the proof. We assume this condition, and from there we reason logically until we're able to conclude that this series under consideration, which has non-zero terms, must converge absolutely. And we used the definition of the limit of a sequence. We used what it means for a geometric series to converge. We used the direct comparison test. We also employed the idea that getting rid of a finite number of terms from a series does not affect its convergence or divergence. And then we also used theorem 9.16. So, and then also the definition of what it means for a series to absolutely convergent. We put all of that together using deductive reasoning to establish the truth of property 1 of the ratio test. And you can see the very last sentence, the proof of property 2 is similar and is left as an exercise. So we just finished looking at the proof of property 1 of the ratio test. At the beginning of the lesson, we began with the ratio test and we looked at some examples. We also understood a situation in which the ratio test would be inconclusive, and that would happen when the limit that we are looking for in the ratio test is equal to 1. If that's the case, you cannot make a conclusion about convergence or divergence using the ratio test, but you would have to use a different test.